Thank you all for being here this morning. I'm so excited to have all of you here. My name is Gopal Sarma, and I'm a physician scientist here at the Broad Institute of MIT and Harvard, where I work on strategy and operations for machine learning. So I wanted to start off by saying a few words about this event, because I know it's an unusual workshop in terms of the mix of ideas, the audience, and the workshop structure itself. Well, in a nutshell, the simple answer for why are we hosting this event and why does it look the way it does is that this event is really about the future and not about the present. As we're going to learn in the next few days, achieving mathematical guarantees of correctness for any piece of software is incredibly demanding. And so the real question is when the overhead is worth it. Now, I probably don't need to convince any of you in this audience that with the increasingly pervasive role played by software systems in modern society, that there are in fact many cases already where we need to build mission and safety critical systems, whether in avionics or the power grid or medical devices. And as automation is poised to transform more and more industries, the corresponding proportion of mission and safety critical systems will also increase. Now, our perspective at the Broad Institute comes from our history in the genomic space. We've known for several years now that the volume of genomic data production globally has been growing exponentially, faster than Moore's Law even. And in fact, there was an interesting paper written just a couple of years ago called Big Data, Astronomical or Genomical, where they predict that by the year 2025, genomic data production will exceed that of astrophysics and even social media. Now, for those of you in the life sciences, you know that there's in fact many other data production technologies that are also witnessing exponential growth. It's not just whole genome sequencing. There are single-cell RNA sequencing, CRISPR-based assays, cellular imaging, and an entire spectrum of medical imaging modalities. And the net result of this exponential growth of multimodal data generation in the life sciences and medicine will mean that over the next decade, we will see the life sciences become key drivers of progress in machine learning and AI, and give rise to an explosion of software systems, many of which will be mission and safety critical. Now, that's the perspective coming from the Broad and the life sciences. But actually, there's only a couple of us in the FMIE program committee that are coming from the life sciences and medicine. And when we got together some time ago to kick around some of these ideas, we actually decided to take a step back and ask a much broader set of questions that were domain agnostic. How does one build mission and safety critical software in any domain? What are the techniques that one can employ? And when you decide to move forward with this incredibly rigorous process, what is the overhead? And our thinking was that by making this workshop domain agnostic, what we're really doing is to begin the process of starting a long-term conversation. Our belief is that whether it's 3, 5, or 10 years from now, by starting early on bridging some of these unlikely communities, when the solutions are needed, that we'll be able to connect the right people to the right problems. Now, I'm the first to admit that I think it's very unlikely that most of you leave this workshop doing formal proofs left and right, and that's totally okay. It's almost by design. But what we do hope that we'll have accomplished is to spark some intellectual curiosity, plant some key intellectual seeds, and most importantly, jumpstart some relationships so that we can work together in the coming years and decades to tackle some incredibly ambitious problems and ones that I think will be very consequential for all of society. Okay, so with that, why don't I go ahead and introduce our tutorial leader, Phil Zucker. Phil is a theoretical condensed matter physicist by training and has since made a name for himself as an expert in functional programming, formal methods, and I think an all-around tackler of challenging engineering problems. Phil currently works as a senior computer scientist at the Draper laboratory. So with that, let me go ahead and turn it over to Phil.
Yep, as you said, I'm Philip Zucker, and I want to take a moment to thank Gopal for setting this all up and arranging it. Like, organizing something like this is a tremendous amount of work. Sometimes you don't realize that until you sort of see it happening, and he's done an incredible job. Okay, so I guess I could wait a few minutes. The tutorial is supposed to start at 9. But in the meantime, let me point you all to the GitHub repo that has a tutorial notebook. We're going to be doing it together in a collab notebook. So here's the repo, and click on this nice, cute little blue badge over here to open up the Colab notebook. And click on the Z3 tutorial link in the center there. Okay. Well, we got a lot to do, so I guess I can just get right into it. So hello, everyone. I'm Phil Zucker. As Gopal mentioned, I work at Draper Labs. So professionally, I use Z3 as backend for tools like the Comparative Binary Analysis Project, which we have open source on GitHub there. It's a tool that takes there's binary programs that there are other tools that perform binary transformations on them. So they insert checks, or they try and fix it in some way. They try and instrument it in some way to like see when bad memory accesses happen or something. And what we do is we lift those programs through a project called BAP, the Binary Analysis Platform, and then we reinterpret them through Z3 in order to determine if after the binary transformation, they still do what they used to do. Or if they do is they are the same as much as you want them to be the same. And then beyond professionally, I just find Z3 and SMT solvers and theorem proving generally just sort of a fascinating topic. That's sort of how I ended up here. As Gopal mentioned, my original background is in physics, and I've sort of just almost completely shifted my energies to formal methods at this point. Gopal gave a beautiful high-level overview of sort of what are the motivations of formal methods and sort of the concerns that we're trying to address with them. But I think it's useful for me to give a little bit of sort of my high-level perspective of what they even are. So really broadly speaking, to me, formal methods are the application of mathematical thinking to computational systems. Now that's really broad. Like you could arguably say maybe the entirety of computer science is the application of mathematical thinking to computational systems. So a little more narrowly, perhaps too narrowly, but I think this gives at least a little bit of better picture. Formal methods make the connection between specifications and implementations more rigid and reliable. So a specification is a precise, clear, and succinct statement of what a program or system should do. The specifications I have in mind often have a logical or mathematical flavor to them. And that's because logic and mathematics are they're designed to be extremely precise languages, and they also tend to be very succinct. An implementation, is an actual program, let's say, that you wrote in C or something, is also very precise in its own way. It's literally what you want the thing to do, barring undefined behavior. Well, maybe it's precise. You don't understand exactly what you're saying when you write the implementation. Can sometimes be a problem, but it's often significantly more verbose than the specification. The implementation has all this extra detail that actually describes like how the system's doing what it's doing. And that can, remove a lot of clarity from what the implementation actually does. Implementations often have more of a programming flavor. Now, these are just sort of rules of thumb. Actually, a specification can be just another program in a programming language. Maybe the implementation might just be sort of a high-level model of some kind that still has kind of a mathy flavor. But typically, they have those flavors. Now, the specification and implementation should be equivalent in some sense. And the process of showing that is verification. And this reduces the possibility of bugs in implementation to bugs in the specification. And in that sense, the program is correct. So how do we actually show that these two are equivalent? Well, we could have like code review. We could spend a lot of money and get some people who are very careful and you trust a lot to go over the two and say like, yeah, we're pretty sure that these two are the same. But it's a powerful approach or a useful approach to try and automate this thing. And that's pretty hard. Like the questions that come up here are very difficult questions that come up during this process of showing specifications, implementations, or talking about the same sort of thing. But one astonishingly powerful and versatile tool that we're going to be talking about today is the Z3 theorem prover. So what the heck is Z3? Well, you can Google it and you'll get the sentence. Z3 is a state-of-the-art theorem prover from Microsoft Research. It can be used to check the satisfiability of logical formulas over one or more theories. Z3 offers a compelling match for software analysis and verification tools, since several common software constructs map directly into supported theories. So what the heck does that mean? Z3, there's a bunch of capabilities Z3 has, and you could sort of see analogies to some other systems that maybe you're more familiar. It has some simplification and algebraic capabilities that are similar to Mathematica, a very light version of Mathematica. Some capabilities that overlap with things that feel like constraint satisfaction solvers, things that solve Sudokus, in a sense, is sort of what they're geared at, like a mini-zinc. And it has the capability to manipulate and express logical statements. And that's something that interactive theorem provers can do, but it's something that's a little more rare, a rarer capability. Anyway, the sum total of those capabilities allows Z3 to effectively and automatically find solutions to a wide variety of problems, or, very importantly, effectively and automatically show that solutions do not exist, to exhaustively not find a solution. So Z3 was designed with the intention it's going to be used for software and hardware verification tasks. And a ton of tools out there use Z3 or some equivalent solver to do the heavy lifting. The other tools are kind of often just translators. They're interfaces that take the problem at hand and just dump it into Z3. Now maybe they sort of orchestrate a bunch of queries, and so there's still non-trivial work doing there. But Z3 is like the bedrock of sort of their actual solving capabilities. So sometimes you might be using tools like those, but it's also interesting just to know how to use Z3 bare, on its own, to develop your own tools, perhaps, or it's sort of a useful Swiss Army knife that surprising the things it can be useful in it. Like I was doing this puzzle hunt a couple weeks ago, and like some of the problems were kind of amenable to Z3, so I just whipped it out because I'm used to Z3 because I made this tutorial. So Z3 is open source. It's hosted on GitHub. It has official bindings for a bunch of languages: C, C++, Python, .NET, OCaml, Java. Tends to be bindings available for most common languages. It's a very popular system. It also has a command line interface that takes a standardized logical input format called SMT-lib. And if you do things in that way, you can also try out different SMT solvers. So if you click on that link there, there's a whole organization, SMT-lib and SMT competition, that shows sort of comparative performance of sort of similar solvers. But Z3 is really just like an excellent default. If you're not sort of specializing to something, Z3 is kind of the place most people turn to as their first choice. The Python bindings are excellent. They're like first-in-class Python bindings. And it's a familiar language, I hope. People tend to encounter it. So that's our choice of the bindings we're using today. So let's just get right on into it and just like do something really simple in Z3. So first, you need to install it. You can click these play buttons to run these cells if you've never used a Jupyter notebook before. You need to do pip install Z3 solver, Z3-solver, because unfortunately someone already sniped pip install Z3. That's something else. Okay, we do that, and then for the purposes of this, like to just import everything in Z3 into the namespace. That's what this line does. And if your notebook crashes or you need to restart your notebook, you need to come back and rerun this line to be able to run everything else. Okay, so the very most basic Z3 problem, what you do is you declare your variables, you state a set of constraints you want to hold, and then you call some sort of solving function. So here we are making two integer variables. x and y. And then we're stating 3 constraints. We want an x greater than 2, a y less than 10, such that x plus 2 times y is equal to 7. And if you run that, it does come back with a solution, y equals 0, x equals 7. And if you plug this back into our constraints, 7 is indeed greater than 2, 0 is indeed less than 10, and 2 times 0 plus 7 equals 7. So it did, in fact, satisfy all the constraints. There's an alternative form to query a solver, and this is sort of the more powerful interface. This is sort of a shorthand convenience function. You declare your variables, you create a solver object, and then you can add the constraints one by one. You call s.check, s being the solver, which can return it'll return different results of the process. In this case, it returns sat, meaning satisfiable. And in the case that it is satisfiable, you're allowed to call s.model, which will return an object that contains this information. This doesn't actually return the model, I believe. I think it just prints it out. So that can be useful. Okay, so that's the basic thing. That's sort of what we're going to be doing all day, all morning. But here's a sort of different feeling thing that you can ask C3 to do. You can also use it to prove properties and theorems, and we'll get more into what that means later. So here we define a variables. That part's the same. P, a Boolean. We define a theorem that we want to talk about. The simplest, true theorem. P implies P. And there is printing it in a nice little mathematical notation for you. And you can call a convenience function called prove. And if you click on that, it does say proved. P does imply P. But if you ask it to prove a theorem that's not true, Z3 can supply a counterexample, which is very useful for understanding why it's not true. So here we have a false theorem. Q implies P. Just because Q is true doesn't mean that P has to be true. It's just, P can be false and Q can be true, and that means this thing isn't a true theorem. And in fact, if you ask Z3 to prove that, it gives that counterexample that even if Q is true, P can be false, and that this will still evaluate to false. So this just isn't a theorem. Okay. So let's talk about some of the more variable types that you have available to you besides just integers and booleans. So yes, you do have booleans. Here is an alternate syntax for getting a boolean, that sometimes things don't have as nice a wrapper function as this, and you have to make things using this const form. There's a convenience function for many of them that has a plural form, bools, and you give a space-separated list of variable names. And that's useful to save little typing, save little space. There's also real numbered variables, and that's very interesting to me. Sort of as a physics background, a lot of problems that I find really interesting involve like real numbers. Integers, bit vectors, which is different from integers. These are the mathematical integers, and these are this is a 32-bit bit vector integer. Floating point numbers are available. You also have arrays. Here I'm showing an array whose domain is integers, and the codomain is going to Boolean. So it's an array of Booleans. And that's a decent basic list. There are more. There's you can make algebraic data types. You can make uninterpreted functions. There's some other things, but this will get us through today. So there are also sometimes you want to take Python constants and turn them into Z3. Mostly this happens automatically, but every once in a while it'll throw an error. It's because the automatic conversion didn't work and you need to manually convert them. So you do that with these val functions. So there's bool val, real val, int val. This will make an exact rational number, which is nice. There you go. Okay, so how do you sort of make operations on Z3 expressions in Python, and how do you specify constraints? Well, it's mostly pretty intuitive, so I'm not going to belabor this for too long. It overloads the right stuff, basically, the Python bindings do. So if you have these a real variable, you can add the real variables, you can multiply real variables, you can take powers, kind of just all sort of what you would expect, I hope. Now, the Boolean operations have these functions, these capitalized, Boolean connectives. Unfortunately, there isn't overloading for the Boolean variables, and that's because, well, I think this is because the Python keyword and is not overloadable, and the ampersand symbol operation is sort of a bit vector operation. So maybe it'd be a little confusing to have that apply to Booleans also. In any case, by default, you need to use these sort of longer form to specify Boolean operations. And then constraints, there's equality constraints, there's not equality constraints, there's inequality constraints, less than or equal to's. And then you can also, since constraints are Booleans in Z3, this does return a Boolean Z3 expression. You can also combine them using the Boolean connectives, which is important to build compound constraints. So with that, I think we know enough for you guys to do the very first exercise. So we have a polynomial here, just a random polynomial taken out of a sack. And here is a plot of it. And we can see that there's probably a solution. There's a zero of this polynomial somewhere around here. Can you find that root using Z3? And then also, if we look at this function, it kind of seems like that might be the only solution. It's not clear. Maybe something happens over here, maybe over here. Maybe this is actually hitting two roots. Not so clear from this graph. Can you use Z3 to show that this is the only solution? So here is a box made for you that you can fill in. And off you go. Give it a shot.
Do we have the Jeopardy music available to play during these pauses?
I mean, I could hum for you. Is that good enough?
I think I have a kazoo somewhere.
So I'll say my solution in about 5 minutes. Maybe that's almost too much time, but. Or if people could post on the Slack when they're done, that'd also be helpful for feedback.
Can you, I'm actually having a hard time finding this exercise. I see that 8 queens is the first exercise. What am I doing wrong here?
So the notebook has expansions, these little triangles. So you may have many sections unexpanded.
Okay, thank you.
And something worth saying too is for people like me that really don't have experience with Python workspaces, anything that's slightly gray, you can click into it and just type there, and then click on the the play arrow again, and it'll rerun that whole area.
Right. You can click play. There's a bunch of stuff you can click up here. Various features, and also shift enter is usually how I run cells.
Actually, if people haven't been using Google Colab, they might need to make sure they're installing Z3.
Yeah, if you run the pip command, even if you're doing it locally, there is a pip command up here that you can run, and that'll install it if you're on Colab or if you're on your own personal notebook. So solve returns an arbitrary solution. It does not return all solutions.
Are we allowed as students to share how we got it in the chat for other people?
I would wait until everyone's had a chance to think about it.
Okay.
All right, so I think it's time to say how, well, there's a couple of ways to do this. So first off, we need to make a variable. We'll make x. And then, the beauty of C3 is that I can just copy and paste this valid Python expression. And I can just say solve, boom. And that gives me, in fact, the root is -1, which looks right. Okay, and so there's different ways. Everyone's free to share their solution on the Slack. There's different ways of showing that that's the only solution. So having seen that it's -1, I can add the constraint, give me a root that's not -1. And that'll say there's no solution. Or another way of going about it, which is illuminating, is you can write this as sort of a proof form. So I want to say, under the assumption that this polynomial holds, is x always equal to 1? Okay, or -1, sorry. And that will come back proved, which shows that there is no solution to this. I've also seen a third solution, not to belabor the point, but you can also do this sort of without having to know what the, so xy reals xy, you could make two variables that both obey the constraints, and you want to have them not equal to each other, which is it's sort of a related thing. But it shows that in fact, there's not two solutions of these equations where they're unequal to each other. So that's a way of doing it without even knowing what the solution was, without knowing what the root was. Okay, so there's going to be starred sections, and those are things I'm just going to pass over. Maybe you're free to look at them in your later on, but sort of we have more than enough to cover in this notebook anyway. But here's some other sort of cute, nice little things to know about. I just want to mention where the docs are for Z3 Pi. So these are the docs, and sometimes I figure out the docs exist for something like way later after struggling and trying to explore it in some backwards way, and I really wish I'd just seen it. So these are really complete, or very complete, and you can find out all the sort of other things that I'm not telling you about. It'll tell you that, oh yeah, you can do this. Like you have here's pseudo-Boolean constraints. Here's a short, nice thing for doing sum expressions or product expressions, and here's different sort of floating point stuff and rounding modes for floating point and yada yada. Like there's plenty more in here than we're going to touch today, or I even mention in the hidden sections of the notebook. So there's that. Another useful thing that taught me a lot is there's the Z3 tutorial. So this uses the SMT-lib input format, but it goes, which is not the Python bindings, but it's an interactive thing that tells you sort of how to use Z3 from the SMT-lib bindings. You can learn a lot from here. And then for the Python bindings, this tutorial is really useful. As you can see, I've cribbed a lot. Some of the things I'm talking about today, I've cribbed from different sources. So in addition to that, at the very bottom of the document, you can find references for even more places to learn about Z3 and SMT solving generally. Okay, so as a first theme today of what do we do with Z3, we can just use Z3 to find stuff. Z3 is from one perspective, just executing like a really fast and flexible search to like a constraint satisfaction solver. So it's sort of a thing that solves Sudokus. And from that perspective, it's not clear why solving Sudokus is applicable to program verification, but it's sort of the first thing I think people learn about Z3. And the first thing I understood about Z3 is that, yeah, it's just sort of a constraint satisfaction solver. And it doesn't just have to be like fun, cute little things like Sudoku and nonograms. There are constraint satisfaction problems that have very real applications. You could express a graph coloring problem, which can be used for register allocations, scheduling problems, routing problems. These are actually useful things for business purposes and other things like that. But the puzzles are really fun and easy to explain, so that's what we're going to stick to. So the first puzzle I'm going to show is the 8 queens puzzle. So the 8 queens puzzle is the puzzle in which you have an 8x8 chessboard, and you want to place 8 queens on it such that no queen attacks any other queen. So that means they can't be in the same row, they can't be in the same columns, and then they can't be on the same diagonals as each other. So as you take a problem like that, and you sort of have to think about, how do I express this as like a bunch of variables? That, that's sort of this thing they try and teach you in grade school about taking a word problem and somehow like mathifying it. And that's a tough thing, but hopefully you can figure it out. In this case, what I've chosen to express it as is a variable for every row. And in that variable, the value of that variable is the column in which to place the queen that appears in that row. So here I'm using a Python comprehension expression to make an array Q that holds one variable for every row. And here you see I'm using string interpolation in Python. I'm using all sorts of cute little Python tricks that I enjoy. It's important, you need to name variables different things, because they will smash each other if you name variables different, the same thing. even if you in different calls to declaring a variable. So here we declare the variable, the variables of the problem, the queues. Here is a array of constraints. So we want to specify that for each row, the queen has to be in a column that's between 1 and 8 inclusive. So here we have the queue of that row is greater than or equal to 1, and the queue of that row is less than or equal to 1. And we have the and of that. And sort of implicitly, this we're going to be using this array as a giant and also. So this is one constraint for every variable, but then this is one constraint for every variable in this queue array. And then we also want them to be distinct. We want none of them equal to each other. So there's a convenient function for that called distinct. And so this is a single constraint that's saying all the variables in queue are distinct from each other. And then the most complicated one, which we're not going to go over that much, is the diagonal constraint. And this does indeed express a diagonal constraint. So what we can do is then this is appending all these constraint lists to each other. Solve, in addition to taking many functions in Z3 are overloaded to take both multi-argument format or taking a list, a iterator of arguments, a generator of arguments. So we're giving it a list of all the constraints you want to hold. We can run solve, and it spits out the column location of, we put queen, the row 1 queen in column 5 in this model, for example. And to help visualize it, what we can do is we can take the model out of this thing. We can make a NumPy array where we set the appropriate squares to 1 when there's a queen in it. And we can use Python, nice little Python functions to sort of plot the thing. And we look at this thing, and indeed, there's 1 queen per row, there's 1 queen per column. And it's harder to see, but there is indeed 1 queen per diagonal, or at most 1 queen in a diagonal. So with that, we're on to our second exercise. A classic problem, toy problem in constraint programming is the send more money puzzle. So there's a unique assignment of digits. There's an assignment of unique digits to letters such that the equation send plus more equals money holds. So S is something between 1 and 9, and E is something between 0 and 9. And then if you smash them together like how you'd actually write down numbers, this equation needs to hold. So here I've set it up a little bit for you. Here we're declaring all our variables, all the digits. And then here is sort of the confusing part of how you convert digits into sort of the complete number that represents the entire word composed of those digits. So this is a cute little Python generator expression, miscomprehension. And here the first one, the first digits have the special constraint that they need to be non-zero, because you wouldn't even write that digit if it was 0. And then I have 3 things for you to fill in. Make a constraint that all digits are constrained to be through 0 and 9. Constrain all the digits to be unique. And then constrain send plus more equals money. And off you go.
Sorry, I have a very quick question in regards to the Queen's problem. So we solved for give me one solution, but there's obviously a few solutions. If we wanted to add a piece that says, prove that there are no more than n solutions, how would we go about that? Oh, I think you're on mute, sorry. You're gonna have to repeat that all over, I guess.
Yeah. Well, I didn't get that far. That's an interesting and good question. And there is a section which I'm not going to cover, which I have some other problem. And I want to loop through all solutions. And the basic way you can do this is you get a model out. So you can call s.check, return satisfiable, you get the model out. And then what you can do is reassert back to the solver that you want a solution not equal to the model. So that'll guarantee that the next time you call, you can call the solve more than once, and you can do it after adding more constraints.
I see.
So you can exhaustively do that. In this case, I do exhaustively do that. Or sometimes it's not hard to come up with an incomplete set of constraints. So there's so many solutions, you're not going to enumerate them. And in general, enumerating all solutions is a harder problem in some complexity, from some complexity standpoint than just finding a solution, which is, kind of obvious. Like, yeah.
Cool. Thank you.
And that, that's a sort of a, generalization of basically what I showed in the first exercise, where, I asked for the solution by hand, and then I by hand said, oh, don't give me that solution. I said x not equal to 1 or -1.
Mm-hmm.
I just want to say a lot of Python shenanigans in this encoding. That I, D enumerate.
Well, yeah, I enjoy list comprehensions. I think they're great. Just pretend it's Haskell.
No, it is cool. I agree. Yeah, basically Python really synergizes with, I use synergize. Python works alongside with Z3 in a very nice way.
Yeah, it really is, tour de force of bindings. I mean, people love these Python bindings to Z3. They're incredible.
What's wrong with synergy?
It's corporate speak. He wants to be an independent.
This is a conference.
Trying to pretend it's not.
Yeah, we're trying to pretend that we're, high concept academics. Phil, there's an interesting question, but I don't know the Z3 bindings well enough to answer that. Somebody's asking if they can get the value of send in a model, which I believe is possible by using evaluate. but I just can't remember what the.
Yes.
Okay, so
Um,
just in your solution, could you then demonstrate that
I
as
will
well?
try. We'll see if I remember to do that. All right, so I think, yeah.
I passed it. I used that in my solution. I just passed it in the chat. How you can do that?
Oh, okay. I think I will do my solution now. All right, so constrain all digits. What do we have? Solve or that? Yeah. So that is a simple constraint for being 0 through 9. And this one is, if you know about this handy little function, this one becomes pretty easy. And this one is also given the above. That one's hopefully pretty easy. All right, so that's my solution, assuming I typed it correctly. And it gave me that. So what I can do is this. So in the chat, someone posted a way of doing this. I think you can also do this. Yes. So you can evaluate arbitrary Z3 expressions with respect to a given model by calling this. So this is some wacky expression. If I actually type out what is send, it's 1,000 times S plus 100 times E, and so on. But this is evaluating that with respect to this model. Okay. Now I get
confusing remark. That eval does not return an integer, but it returns a Z3 integer, right? So if you try to then add it to something else, which is what I did, it'll just say, okay, well, I'm returning the symbolic addition and not like a number.
That is correct.
Yeah,
so
but you can use it. So in the previous case, I used it, for example, I had a first constraint that was basically writing the equation. And then I just get the value, and then I added another constraint saying that I want my solution not to have this value. And then you can use it.
Yes, you can use it without getting it into the Python layer and reasserting to the solver. But sometimes it is useful. Like the beauty of the Python bindings is being able to flip in and out of the Python layer with reckless abandon. And there's a section up there that we skipped over about how to get stuff out of the model. And one of the things, you can get an integer out using .aslong, so that returns a Python integer. Okay, so now we have a nice long section where I'm talking at you. So everybody can lay back. So it's really useful, in my opinion, really important to have just at least some rough conceptual picture of what software is doing when you ask it to do stuff, in order to sort of predict where pain points might be, or to formulate your problem in a way that's amenable to the solver. Like if you don't have at least a rough picture of what Z3 actually has in it or what it's doing, I think it's pretty easy to just assume it can do everything and come up with a way of asking the question that it's not going to be so happy with. So Z3 and other SMT solvers, SMT meaning satisfiability modular theories, are built around the core concept of a SAT solver, satisfiability solver. So let's discuss that first. So the context for a SAT solving is that you are talking about propositional logical formulas. So a propositional logical formula is a combination of Boolean variables using Boolean connectives like and, or, implies, and not. And so here's a propositional formula over the variables P, Q, R, and W with Boolean variables in mathematical notation. You may not have seen this notation before. I think this was pretty new to me at a certain point. So this V is the mathematical notation for or. This TP is mathematical notation for and this sideways L is mathematical notation for negation, not. So this is saying P or Q and P or not W and W or R or P and so on. And so if you assign values to those variables, you can evaluate the formula to determine if the whole thing evaluates to true or false. So in that sense, formulas are kind of talking about the same thing as a Boolean circuit is talking about. And also, you can think of this, one way of interpreting what this means is as a Python function that evaluates the same thing. So this Python function takes in variables P, Q, R, and W, Booleans, and then it would evaluate, this is the same formula put into Python notation. So one useful question you can ask about a propositional formula, and there are others, is if it's satisfiable. Satisfiable means there exists an assignment of Boolean variables to true or false values that makes the entire formula evaluate to true. So from a circuit perspective, this is sort of asking us to run the thing backwards. We're like, we want to make the output of the circuit true, and then try and figure out what the inputs of the circuit have to be. So there's sort of a deductive process happening there, or a guessing process. And likewise for this Python function, Python, by its nature, does not offer the ability to sort of run this thing backwards. So specialized solvers for that particular question are called SAT solvers, one of which is in the core of Z3. So here's a Z3 query that sticks to just the SAT fragment of its capabilities. And it's a translation of these two things into a Z3 query. And it'll return a value of P, Q, R, and W that you could plug back into this Python function, and it would evaluate to true. Or it might return saying, actually, there are none. This thing is never evaluated to true. So given a satisfying solution, it's easy to check. You plug it back in to this Python function. And it's that property that it's easy to check is what puts it into the complexity class NP that sometimes you hear about in these P equals NP questions conjecture. In principle, it's simple to solve a SAT problem. In principle, you can do it by brute force search. It's obvious that'll work, that if you have a giant nested set of for loops, picking out every possible value for P, Q, R, and W, try them all, plug them into this function, see if it comes out true. That will enumerate every possible solution. You're definitely going to find one if they're going to find the satisfying assignment if there is one. And if you get through the whole thing and never found it true, then you know there isn't one. But that method does not scale. For every variable you add, you're multiplying the size of your search space by a factor of 2. So the brute force becomes totally unacceptable, way below 100 variables. So SAT solvers go about it in a smarter way. That's like the silliest, most brute force way you could go about it. They try and deduce and propagate information, kind of similar to how a human solves Sudoku. And so that technique's been around a while, this sort of propagation technique. But a revolution in SAT solving power sort of occurred in the 90s and the aughts, where new techniques were found, some of the most prominent of which are back jumping, two-watch literal technique, conflict-directed clause learning, and random restarts. And there's an interesting resource to learn more is Armin Bier, who's one of the world premier experts in SAT solving, gave like a massive gave a massive tutorial on sort of what sort of modern techniques in SAT solving and going over like the code of his SAT solvers a little bit. So that's a really interesting resource. And that came out just on Monday. So there's a surprising number of useful and interesting questions you can encode into the form of some Boolean formula in order to leverage the power of these SAT solvers. Like they're so good that it's worth twisting your problem and getting into the SAT form, because you can just take a SAT solver off the shelf and there's a decent chance it'll beat the pants off of some customized solver. One natural application is hardware verification of logical circuits. I know that they're Boolean circuits, and it just makes sense that some sort of Boolean-y solver is going to be useful there. But SAT solvers have also been used to prove mathematical conjectures and combinatorics and things like that, previously unknown mathematical conjectures. Okay, so that's a whirlwind through SAT solving, which is a deep topic of itself. How to actually do it is a really deep topic. But now we're going to put another layer on top of that and talk about SMT solving. So satisfiability modulo theory. So there's sort of, I like to think about it as a sort of 2 layers the SMT solver is working at. There's sort of, the problem at hand sort of has a complex Boolean logical structure of ands, ors, implies, all those connectives. There's a bunch of that, and that would be hard in and of itself. But then there's also sort of this domain-specific structure of talking about inequalities over the reals, or addition and multiplication and things like that. And sort of the basic gist of the methodology that SMT solvers use to approach these problems is you can abstract a complex fact like x plus y is greater than or equal to 7. That fact is either true or false, okay? So you can abstract that fact as an opaque Boolean variable p. And if you do that to all the facts in your problem statement, what you're left with is a propositional formula. And then you can throw it into a SAT solver, okay? So then the SAT solver comes back with a satisfying assignment. And then you need to look at the satisfying assignment. And maybe it says that P and Q are both true, but P was x is greater than 10 and Q is x is less than 10, okay? But those two things, because of what those opaque Boolean variables actually meant, that's actually not possible. And the reason that happened is because we did take this abstraction that sort of just the pure abstract Boolean formula does not capture everything about it. It is an abstraction of what we're actually talking about. So as we were discussing earlier about reasserting things, this is a general technique of sort of getting models out of something or solutions out of something, figuring something out, and then, oh, there's actually a new constraint we need to know about. So in this case, we know that P and Q, these two mutually exclusive things, actually they can't be true at the same time. So we have that we would reassert a constraint to the SAT solver, the Boolean constraint that P is not equal to Q. And then you iterate that process over and over and over again. And eventually the SAT solver gives you back an assignment that works according to your actual interpretation of the formulas, or eventually you've asserted enough formulas to the SAT solver, extra formulas, that the SAT solver says unsat, and it knows that even in the Boolean logical formula, the thing is unsatisfiable, in which case the whole thing is unsatisfiable. And so this is where the intimidating name satisfiability modulo theories comes from. It's sort of a SAT problem mod the actual understanding of the theories involved. So in actual SMT solvers, there's no reason to like hamstring yourself with like this sort of like external SAT solver, and then like it comes back with a thing like these layers are more intertwined than that. There's no reason to be so lazy about it. And I mean, the gloves are off. The solver community will do anything they can to make these things faster. So it's a little more complicated when you actually have an actual SAT solver. But that's the basic idea. So again, it's helpful to know sort of what are the domain-specific information that Z3 likes and can handle. So it understands Boolean stuff using the SAT solving procedure. But then the domain-specific stuff, it just has built-in understanding of certain kinds of problems, and then ways of getting those problems to sort of talk to each other. So for example, Z3 has a understanding of linear equations, and you can solve linear equations using Gaussian elimination, and Z3 has something like that inside of it. And linear inequalities, Z3 has something like linear programming inside of it. It understands bit vectors, which you can reduce to SAT problems by bit blasting, or maybe it has some other tricks that it's using. Arrays, algebraic data types, it does understand polynomial equalities. Try and avoid them if you can. Once you go from linear to polynomial stuff, it's a big jump in theoretical and practical complexity. So it's not going to scale as well. So these pieces give Z3 a surprisingly powerful and flexible base to work from. Each of these on its own are sort of like, yeah, linear equations. You can do a lot with linear equations, but maybe you can't verify a whole program. But once you start like weaving these things together with a little bit of cleverness, like it's absolutely amazing what you can get this thing to do. But Z3 can't do everything. You can express way more things to Z3 than Z3 can actually solve. I've been cherry picking problems I know it handles well. So here's an example that sort of a priori knows Z3 just can't handle at some scale. factoring integers is a problem at the heart of RSA cryptography. So if Z3 could factor big integers, Z3 would break RSA cryptography, and RSA cryptography is not currently broken at some scale. But you can make two integer variables, make a public key that's the product of two primes, and then make the constraint that you want the two factors of this number, and it does work. But if you have a slightly larger example, this will just churn and churn and churn and won't return to you. Okay. And again, as I mentioned, nonlinear equations are going to be tough. And here are some issues where, like, sometimes things come up that are difficult to even express to Z3. So some nonlinear functions like exponentials, sines, cosines, logarithms, Z3 doesn't support that. Other SMT solvers might, or you might find some way to sort of trick your way into encoding that into Z3. And also sometimes Z3 does support like powers, but it doesn't support this. If I hit this, it comes back unknown. So again, this is because really Z3 wants to talk about polynomials. It doesn't want to be talking about exponentials. That's the thing it really understands how to do. So if you didn't know a little bit about what Z3 actually does under the hood, you might, this is still maybe a little surprising, but it doesn't support everything you can write down. Yeah. All right. So with that, I think we'll still start this section, and we'll take a coffee break pretty soon if you're getting tired. So we've been talking about using Z3 to just find stuff, but what does it mean to have Z3 prove stuff? Well, basically, in this context, what proof is exhaustively not finding counterexamples. So you're still, in some sense, searching for something. You're searching for a counterexample to a theorem you have. But if you don't find it, if you exhaustively don't find it, then you actually know that that's a true theorem. Okay, and that's the general paradigm of sort of proving in the context of Z3. So you can call, so the way you do is you take the way to encode this is you'll take a theorem, you encode the negation of the theorem, and then assert it to the solver. And what that's doing is it's trying to find an assignment that makes the theorem not true, i.e. a counterexample. So if solver.check can return different result codes. It can return sat, meaning it found a solution, unknown, and that means I give up, in which case you haven't proven or disproven anything. And it can also return unsat, but unsat means Z3 says, I know there's no solution. I know that in some sense I've tried everything. Like I've determined that, no, really there is a reason that there is no solution. And so the contents of that prove function I showed much earlier is actually very simple. It's actually, this is essentially the contents of it. It makes a solver, it asserts the negation of the formula you gave it, and then it checks if it's unsat, it prints proved, otherwise it prints failed to prove. Or if it gets sat, it prints the counterexample. Okay, so here's a short reminder on how you make these propositional logical formulas. And here was an example, a different example actually from what I showed earlier. That if you have both P and Q are true, that implies P is true. Okay, so that's a true theorem, and you can ask prove, and it'll prove it. And with that, we're ready for our next exercise. I have a set of Boolean theorems, and I want you guys to try and prove them. All right. I think I'll write down my solutions and then we're going to take the coffee break. So, ooh, all right. First, I need to declare my variables just to be sure. Get in my way. How are we doing? There we go.
I have a short question.
Yeah.
Is prove the equivalent of check not?
Yes. Yes, it basically is. In fact, you can find the source code for it. There's the source code for the actual prove. It is just a small wrapper. And you see that, in fact, s.add the not of the claim.
Yeah, okay. Yeah, okay.
Yep. Where was I? Here we go. So this is the sort of classical correspondence of turning implies to an or, which is a useful thing to know about. Very good. And then the last one is Peirce's law, which is an interesting, again, theorem in classical logic that in some sense corresponds to continuation passing, which is a pretty interesting little side note that we're not going to talk about. Proved. All right. So with that, we'll take the coffee break. You're welcome. We'll still be talking on Slack, and you can all go to the Gather Town to chat and stuff. And I'll see you in about 20 minutes. So let's say 10:25. And we're back. So to keep get those brain juices flowing again, we're going to launch right back into another exercise. So this exercise is proving some simple properties about the integers and the floats. So, two common properties to talk about is that addition commutes, addition is associative. There's the law of trichotomy that x is either less than, equal to, or greater than 0. And x times x is always non-negative. So here I've set up 3 real variables and 3 floating point variables. And your job is to prove or find counterexamples to these 3 properties. ignore me if you like, but there's a question about how do you extract a floating point from Z3 floating point. And here is how I figure these sort of things out. I use the dir Python function, and then I look through all the methods that are available and see if anything looks spicy. It's possible that such a thing is not supported. So it looks like you can extract the exponent and the mantissa, is that what the other thing's called, as integers. So it doesn't directly go to a float, I don't think, but you can get the pieces out. All right, I'll do my solutions. So, I mean, basically, it's nice thing about Z3 is, and these bindings, is it's very straightforward to just copy and paste these and get these different properties. And indeed, over the mathematical reals, you shouldn't be too surprised that they are, in fact, associative and commutative. And trichotomy. Yeah. And x times x is equal to 0. All these things are true. And I can just copy and paste this down here. And it churns for a little bit. And, you know, maybe this is surprising to you if you think of the floating points as real numbers, which I usually do. I mean, that's the whole point of them. But they are associative, but they're not even, or they're commutative, sorry, but they're not even associative. Floating point numbers are not associative because different roundings happen in the different orders. And they don't obey the law of trichotomy because the inequality operators on floating points and equality don't work kind of how you might naively expect them to. And likewise, that's sort of the same issue with assuming x times x is greater than or equal to 0. So, you know, if you think of floating points as real numbers, it's not so hard to write a program that makes perfect sense for the real numbers, but does not work for floating point. There's a subtle bug there. If you had this check in some if statement or something, like there is a way for that thing to go wrong.
Sorry, I missed the first part, but all these kind of like rounding problems that do you have, are they the same kind of like rounding problems that you would have with floats in a real machine? Like, for example, if I have this kind of like counter examples, can I expect the same happening in C?
Yes, I think so. These floating point numbers in Z3 are basically the bit vector models of floating points. They're sort of modeling like the IEEE spec of what floating point does.
Right, they're designed specifically to get the same counterexamples as in C. But there are some subtleties, which is like Phil said, IEEE spec, which says very specific things about how floats should behave, and not necessarily about how they do behave on all hardware. And C, I think, requests the IEEE spec to be satisfied. But there are some ugly little caveats, which is that the IEEE spec isn't completely precise on all values, stuff like that. So there's much debate about the semantics of floats in SMT solvers, and that's all handled by the the SMT-lib committee. So they have long debates about what all these things should mean. But for the most part, it is what C does.
Floating points are complicated, and Z3 does its job to support the spec, but not everything goes according to the spec. So there could be more counterexamples, etc. Also, as a personal anecdote, you notice I took float 16 here, so it didn't take so long. I haven't found SMT solvers with bit accurate stuff to scale that well on floating point problems I've tried, which is too bad, but it's a hard problem. Okay, so now we finally have enough tools. We sort of talked about toy little puzzles or sort of things that felt like kind of pure math, proving propositional formulas and things. But now we have enough tools in our toolbox to attack problems that really feel directly related to programming. I guess that floating point one was also a pretty programming heavy thing. So there's a really fun example that I took inspiration from a Z3 tutorial. So there's this website a fun website to check out that has a bunch of bit twiddling hacks that, integers in a computer are not the mathematical integers. They're represented by these bit vectors, these, a sequence of bits that's 32 long or 64 long, and they have a particular way of encoding actual numbers. But you can abuse these, you can abuse that the representation of these numbers to achieve in fast ways certain operations. And so here's a big pile of them. Now, should you actually use these tricks? Very questionable, partially because compiler writers have seen this webpage, and the good ones, the ones that actually work, they already threw into your compiler. And the ones that don't work, well, you shouldn't be using them anyway. They don't work in the sense that they're slower than some naive ways of doing it. So, if you're actually using these tricks, you might be obfuscating your code for absolutely no reason. But nevertheless, they are cool. And some of them are useful. Some of them the compiler won't do. So here's one example of a bit trick, power of 2. So it's a check if a machine integer is a power of 2. And to understand this hack, it helps to look at the Boolean form of these numbers. So if you take a power of 2 here, 2 to the 13, and you write it out in binary, you see that it's all zeros except for a single 1. That's what a power of 2 looks like in binary. Okay. And then if you subtract 1 from it, you see that the most significant digit changes. Like when you have a power of 2 and you subtract 1 from it, that has to flip, and then all the other ones change. And in fact, that's the only time that x and x minus 1 have a differing most significant bit. Because if you have something that's not a power of 2, all the change happens down here, and the most significant bit stays the same. So a fast bit vector trick for checking if Booleans to check if integers are a power of 2 is you can just take the bitwise AND of these two numbers. In this case, you'll get 0 because you can see here that they don't share a 1 in any position. But here, a non-power of 2, they're always going to share a 1 in the most significant bit of the number. Okay. So I have two forms here. I have a naive, slower form of checking the same thing using a range expression, using a list comprehension expression in Python. Just all the powers of 2 in between 0 and 2 to the 32. And here's the fast bit trick form of it. And I can run some tests. So I want to check that, like, yeah, this bit trick actually returns true for every power of 2 in this range. And then I have a nice randomized test. It takes a little bit of time, but I just ran 100,000 tests, and I was checking, making sure that they agreed in every single one, and printing any of them where they don't agree. So like 100,000 tests, that's pretty good. That gives me a lot of confidence. But cherry on top, let's make Z3 confirm the same thing. I assume it's all going to work out. Oh, well, yeah. So I took I made a bit vector variable. I encoded the fast form. I encoded the slow form as an OR of all the possibilities of the powers of 2 in this range. And I wanted to prove them equal, but it gave me a counterexample. But I ran so many tests. 100,000. Is this right? Yeah, they actually do return different values. So what's going on here? But okay, so if 0 is not a power of 2, it should return false. But if I subtract 0, if I subtract from 0, something weird is going to go on. It's going to do some sort of weird wraparound behavior or something. So maybe I can exclude that case. So we can make a separate thing, a separate form that explicitly checks for the 0 case, which is a problem. There's a weird wraparound effect there, but otherwise it's probably right. And when we check that version, it does indeed prove true. And this is the version that's actually in that webpage. I played a little trick on all of you by removing the little maybe non-obvious condition in the first part. Okay, so with that, I think you're ready to try a similar problem. So here's a bit trick that checks if in 2 numbers, if exactly one of them is negative, okay? And the reason this works is when you're representing a negative number as a bit vector, it uses something called 2's complement usually. And the most significant bit of the entire bit vector, like bit number 32 in a 32-bit integer, is what's known as a sign bit. So that bit is 1 if it's a negative number and 0 if it's 0 or a positive number. So what we can do is we can take the XOR of 2 bit vectors, and that will take the XOR of that sign bit. Okay. So if only one of them is negative, that XOR will return a 1 in that position. But if both are negative or both are positive or 0, it'll return a 0 in that position. So you can then check if that bit is set basically with a less than check. Basically, the less than 0 check on a number is basically just checking that bit. So here's a fast version of that, and then here's the slow version. Well, probably not that much slower. That it has branching behavior. All sorts of things that aren't ideal. The more naive version of saying it. And here are some tests, a very small number of tests, just saying the ones for which it evaluated to true. And they do seem to be the ones that have only one negative number in them. So your job is to turn these 2 functions into Z3 specs and prove their equivalence. All right, I think that's enough time for me to give it a shot. All right. So one way of doing this is we can directly translate the form I gave above. Using the if then else construct of Z3, which I have not shown, I think, actually. But the first argument is the expression that you're if then elsing, and then it's the then case and the else case. So this returns true if otherwise, and x greater than 0, y less than 0. Yes. Proved. There's also, you could, another way of specifying this rather than using that is a more logical flavored version of it. There's two cases that you want to be true, return true on. It could be return true on this case, or it could return true on this case. And that also proves. So those two, actually, we can show that slow and slow 2 are equivalent directly. Okay. XOR, yeah. So Slack mentioned another solution that sounds good. You could also use that. Okay. So next topic. So it's fairly straightforward with a few tricks to translate programs kind of directly into Z3 expressions. And depending on the community goals and differences in sort of a search strategy they're using to do this, this can go by the name of symbolic execution or bounded model checking. At the very coarse level we're looking at these things, they're kind of more or less the same thing. But there are differences between them. And here's some real world projects that are interesting to check out that do symbolic execution bounded model checking. There's the CLI symbolic execution engine. So that actually, these are real systems that CLI operates in like the LLVM toolchain. So it'll actually take code, I believe C code, and C++ maybe, maybe other ones. And it tries to use Z3 and symbolic execution to find bad pathways through the code that lead to crashes or other bad conditions. Another tool is ESBMC, bounded model checker. This is another model checker that sort of takes C code and can prove properties about it through bounded model checking. And here's another interesting system that uses Z3 as a bounded model checker for TLA+. So that's not C or C++ code, but now it's using Z3 in a bounded model checking thing for sort of a TLA+ model of your system. Shout out to Hillel Wayne. So let's go a little bit about how you might go about how these things sort of look. So here is a very simple program. A random program. We take in a variable x, y is equal to 2 times x plus 4, z equals y times y. We want to assume z is greater than or equal to 0. It's obviously true to us because z is the square of something, so it's greater than or equal to 0. So this is correct. And then we return z. So I can directly translate this to Z3 with very few changes. So I see all the variables in here. You know, in C, for example, I would have to declare them all. We'll have to declare them all here too, because I'm using Z3. I declare X, Y, and Z, and then I can go line by line basically and just translate it into Z3 constraints. Okay, so there's that, and then I can ask Z3 to sort of prove that the output condition is always true. So I asserted the program, we're assuming it's constrained by what the program actually does. And then we are searching for a counterexample for z greater than or equal to 0. And it returns unsat, which means that it proved it correct. Now consider this slight variation of the program. To a Python programmer's eyes, this is the same thing and maybe better. It uses less confusing variables. Why have so many variables flying about or something? But then when we try and directly translate this program into Z3, I would do it like so, naively following this example up here. But this is not right. This is the difference here is that the issue between assignment and equality. Equality is a slippery concept, and there's slightly different notions of it. And this isn't just Z3. This occurs in Python too. Consider these two expressions. Well, one's a statement, one's an expression in Python. The first one would set variable x to the number 3. The second one is a check. It returns a Boolean if x holds the value 3 and of true, and returns false if x doesn't hold the value 3. And you might, to a beginner programmer, like they could get hung up on this. They'd be like, they're both equality. They're both equality. Like I don't get it. But I mean, if you've done a little bit of programming, you're aware that these are two very different things. And the same thing is happening in Z3. The Z3 equality is really distinct from both of these two. It's closer to this one, but definitely pretty different from the notion of assignment as an equality. Z3 is kind of static. It has no intrinsic notion of time or mutation, and its expressions are more like what's taught to you in a math class, or like, they teach you about y equals mx plus b, stuff like that. You wouldn't write down y equals mx plus b and then y equals 7, and then assume y equals mx plus b no longer holds or something. You know that both hold. So when you're modeling a programming language with mutation in Z3 and you're modeling assignment statements, you need to translate the mutational equality to Z3's notion of equality. And the basic trick to do this is to replace, every time you assign, make it a fresh variable that you're assigning to, rather than overwriting a previously assigned variable. So you can automate this. This is a straightforward trick. If you look at what I did here, is I took this program, and then every time there was an assignment, I just updated a counter and appended it to the name. And then if you rename these variables, we're back to my original example, of course, with y being x1 and z being x2. And now we're free to directly translate again naively. So this transformation isn't just something that occurs in our silly formal methods stuff. It's related and very similar to a transformation known as single static assignment. And single static assignment occurs in compilers you use. The LLVM intermediate representation, for example, is a single static assignment form where you can't reassign to variables. The sameness of x at different points of your program is an abstraction that is kind of a falsehood if under a certain model of what you want to think about your program. The compiler is free to take a variable you called x and put it into register R0 or register R7 and move it around however it wants, just so long as it appears to you, the user, as if it were the same location. OK, so then how to describe branching? So branching also takes a little bit of ingenuity, but it is greatly helped by the ability to have this if-then-else construct available in Z3. So here I have another silly program where I have a simple branch. If x is less than or equal to 0, y is equal to x, but otherwise y is the negative x. We square it. We still want the post condition of z greater than or equal to 0. And we can basically translate this program directly into Z3 using an if-then-else construct. Now, if things get more involved with deeper chains of if-then and else's, it's a little harder to sort of track and figure out how these things work, but it is doable. But with that, I've given you sort of, I think this is very exciting. I've given you the pieces you need to prove a sorting algorithm correct. Can you believe that? So the very simplest sorting algorithm is 2-sort. if you're only sorting one element, well, it's kind of not a sorting algorithm. You're just returning the element. But if I give you two elements, you need to return the same two elements ordered such that you know, the thing you're returning, the first one of the thing you're returning is less than or equal to the second thing you're returning. So the very simplest sorting algorithm in the entire world. You can, and here's a simple Python program to do it. You see that I'm using a temporary variable to perform the swap. And otherwise, sort of, you know, if I were writing sort of intuitive Python, I might leave out this else case, but I put it in there to maybe help your minds realize how you should be translating this to Z3. And your goal is to translate this program to Z3 and prove the property that the output in the output, the first element of the output is less than or equal to the second element of the output. And if you want to think about it, after you've done that, does this actually prove, does this property prove this is a sorting algorithm? So a little conceptual question there. We're proving that property, but does that prove it sorts? Okay, I'll start filling in my solution. Yes, so I need to declare all my variables. And I can already see I'm assigning to the same variable multiple times. So I need copies of those variables, as I talked before. And then my program is just directly translating this thing. So the first condition, under that condition, I want temp to equal x. x1, the first assignment of x is equal to y. And then y1 is equal to temp. And in the other case, I want x1 is equal to x and y1 is equal to y. And that's the whole program. And then I'll show a slightly different form of proving this rather than the solver add form. Under the assumption of the program, I want to prove that x1 is less than or equal to y1, I believe is the condition I want. Uh-oh. Just guessing.
So in y1 equal temp, you have a comma?
Oh, yep, thank you. Oh, no.
That's what's nice about programming in real time, especially in front of an audience.
There we go. Well, that's how you know it's real. You know, it's not, well, I do have a canned document over here, but wasn't even looking. Okay, so that does prove that. And so the question, as was mentioned in Slack, this property doesn't really specify that this is a sort in the sense that we want it to mean. Because if you had a function, very bad sort, even worse than some of the sorts have been mentioned in the Slack. X, you know, if I just return 1, 2, this function will also pass the condition we have, but it's not a sorting algorithm. So the extra condition we need is that the inputs have to have, the set of the inputs has to be the same as the multi-set of the inputs has to be the same as the multi-set of the outputs. That combined with this condition, I believe, makes it a sort, for which this one doesn't pass, because you could come up with a counterexample, like if I give you 14 and 20, well, the set of the output isn't the same as the set of the input. Okay. So more fun stuff that we're not going to talk about. But here's taking that to the next level. So sorting networks are a really fascinating take on sorting algorithms. So what they are is they're in a sense an unrolling of a sorting algorithm into a circuit. So you sort of fix ahead of time what you're going to do. And it's a circuit made out of compare and swap. So this diagram, these are the inputs. This is like a size 4 array and the input. And then when there's a dot and a line connecting it, it's a compare and swap operation. So, you know, the compare and swap operation is actually the operation we just built and just verified. It's to sort. And then if you have the correct sequence of them, if you do this sufficiently, the output will be sorted. And you can there's clever schemes for coming up with different versions of these. And here is a trace execution of one, for example. So you could just like dump a big pile of them. In some sense, that's a sorting network version of bubble sort, if you just like did this over and over and over again. But there's things that are more like merge sort, things that, you know, have that sort of n log n complexity that you want from sort. And one particular example is batch or evenage merge sort, which is, you know, it's something. It's complicated. Looking at this, like it's not even clear to me exactly what the pattern I'm looking at here is. And then we have this big pile of Python code that generates this sorting network. And I copied and pasted that exact code over to here. Oops. I need to expand this. I copy and pasted that exact code from, unfortunately, the old version of the Wikipedia article. The new one has some pseudocode that's not Python anymore. But this is the exact code from there. And what happens is if you want a sorting network of size 8, you call this function, and it will generate a sequence of gates, a sequence of compare and swap operations that is the batcher even odd merge sort of size 8 for an 8 size input. So it first compares the 0th and the 1st input, then the 2nd and 3rd input, then the 0th and the 2nd input, and so on. Here's a little fun thing we can do. I can take this exact code. It generates this. This is a specification language. In some sense, it's a tiny programming language for specifying a sorting network. And what we can do is we can reinterpret this structure into Z3. So every one of these compare and swaps, we're going to interpret into picking out those elements and using our toSort, essentially, to interpret it. So here I've made a predicate describing what it means for a list of variables to be sorted. And this, you could have just compare every single one to every other single one and saying that the right order. But here I sort of took the transitivity into account and just saying that something is sorted if each neighbor is sorted. If every neighbor is sorted, the whole list is sorted. And here is a verification function. It builds a solver. It builds an integer variable for every element in the input. And then it executes pairs to compare, which is this program built by this Wikipedia function. It interprets it. It picks out the right variables to compare and swap, interprets it, and puts them back in place to make it ready. We add the verification condition that it's sorted. Now, in fact, using a bit of prior knowledge, I do in fact know this is a sort and not this, just because it's a sort, its ordering is sufficient for it to be sort because compare and swap by construction, the compare and swap operation by construction maintains the set of the input and the output. So since we're only building this thing via compare and swaps, I already know that's true, but that's a little bit of a cop-out, but and there's ways to improve that, but for simplicity, that's what I did. So we can run it. So I can make a sorting network of size 8, and that gets oops, I need to run this cell, and I need to run this cell. So proved. It came back true. And that's that. It proved that this exact network actually does indeed sort. And I didn't need to understand anything about how batcher even odd merge sort works because it's complicated. So here's a reasonable thing you might want then, is you might want to ask, OK, can I prove that Python generator code is true for all n? And actually, that question, it's not so hard to just ask a question that takes you slightly outside the comfort zone of Z3. And that one right there is something that takes you outside of the comfort zone of Z3. Really, in order to prove that a concrete example of batch or even odd merge sort is easy enough to interpret into Z3. But to prove that the generator always returns a correct sort requires a reasoning by induction of some kind. And Z3 is just doesn't really have induction principles built into it. So in fact, a question of that kind is best verified by a tool like Coq, which Cody's going to be talking about tomorrow. But the automation is incredible, and it lets us do astounding things. So here's, we're going to use a verification function we built to do a simple, very naive synthesis of a sorting network, an optimal one, in fact. So an optimal sorting network is one that uses the minimal number of compare and swap operations. So the batch or even odd merge sort is good, but is it optimal? I don't know. So what is, and how could we build such a thing? Well, the obvious, British Museum algorithm for most things is just it's clear enough that we can enumerate every possible sorting network. Basically, we just need to enumerate every possible one of these tuple sequences. The tuple sequences can take 2 wires that are between the input sizes, and then just start enumerating longer and longer lists of these things. And then what we can use is we can use our verification function. We generate every possible sorting network. We call the verification routine. And if it returns proved, then we've found a sorting algorithm. So this is this returns every possible swap for a sorting network of size m. And this returns all networks. So this is the length of the sorting network, the number of gates it has, and then this is the size of the input of the network is m. And then the synthesis loop is we start with a small number of gates because those will be easier to verify and there's a smaller number of them to generate. And we just increase that number up until eventually the verification returns true. And in that case, we return the network. And I should have already been running this because it takes a little while. So it quickly churns through 0, 1, 2, and 3. And then it takes a while for sorting networks of gate size 4, of gate number 4. So we're synthesizing a network with 4 inputs, and we're trying to find one. And it's churning, 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 churning. To cut to the chase, I mean, we'll see it happen, but it returns a sorting network eventually of size 5. The combinatorics of these networks is absolutely disgusting. And this is not a good way of synthesizing. Well, it's good, but it's not a scaling way of synthesizing a sorting network. So you can consider the things, there's no reason to take such a naive approach to generating the networks. There we go, we got one back. So that is a sorting network and we've also proven by this enumeration process that it's optimal because we went through them in order. And actually the optimal sorting network of input size 4 is gate length 5. So we should do early pruning. We shouldn't call the verifier so much. There's some sorting networks that are obviously incorrect, like a sorting network has to touch every single input. We know that for a fact. We should generate that, or we should just quickly exclude those. And maybe there's more heuristics you might have to throw in there. And generally, program synthesis is such a hard problem. Like the space of programs to search is so huge that you really need to pull out all the stops and all the tricks and tie no hands behind your back in order to make these things work. But it is really tempting and pretty cool to like specify the thing you want and then have it come back with a program, and actually a really good program. That's the dream right there. And maybe someday we'll have that at a larger scale. All right, so here's another fun example. Neural networks are all the rage, and I want to get a little bit of that neural network hotness into this tutorial, because why not? So neural networks are, one way of looking at them is that they're just a really flexibly parameterized class of functions. And then what makes them useful is that they can be used at insane scale due to the excellent available implementations and due to their simplicity in some respects that makes it fast to implement. There are intuitive ways to take sort of abstract structures and symmetries of the problem and sort of encode them into the neural network themselves. That seems to be a very important aspect of why they're so successful. And then also inspirational analogies can be drawn from nature. So all those are reasons why they're a very powerful family of parameterized functions. So one common way to construct neural networks are a sequence of linear transformation with nonlinearities inserted in between them. And the parameters are sort of the coefficients of the linear transformations that are occurring in each stage. A common nonlinearity to use is ReLUs, rectified linear units, which they look like this. This is a ReLU function. It's 0 if x is less than 0, and then it just returns x if x is greater than 0. So that's something that can be lightning fast to implement because it's doing very little computation, really. And also, as a nice side benefit, this is actually not the worst function in the world to have in your formal method problem. So when you use ReLUs and linear layers, when you regard the weights as fixed, a neural network just becomes a giant piecewise linear function. And piecewise linear functions are among the functions that are kind of the easiest to analyze, because they're composed out of linear pieces, and we can just crush linear stuff. Like it's all about Gaussian elimination or solving linear equations. That's something humanity knows how to do. And then the piecewise part of it essentially means you can reason by cases. You can just cut the regions apart and take them one by one. Now that sounds great. Unfortunately, the way that the piecewise linear functions in particular that are being generated by these neural networks have like an exponential number of regions. There's a ton of regions. So it's not easy by any means to actually analyze these things, but conceptually they're kind of nice. So another issue that we should mention when we're talking about verifying neural networks in the context of machine learning is that kind of one of the main benefits of machine learning is that they're solving tasks that don't have a mathematically precise specification, which is also something we need as a prior, in order to sort of apply formal methods. We need to sort of know what we're trying to prove or know what we're trying to show. What is the mathematically precise definition of a horse? You could come up with something, but it's gotta be pretty fishy. And that's actually kind of the approach people took in some sense with good old-fashioned AI for many, many years before machine learning sort of overtook that. So the surprising power of neural networks is often in areas where mathematically precise specifications aren't available. And tasks that do have specs kind of feel fishy as at least questionable areas of machine learning techniques. Because A, how do you know the network meets the spec? And also, one suspects that if there's enough mathematical structure to mathematically specify what you're talking about, maybe that's exploitable in some more straightforward way that's like easier to know is actually right. However, there are a couple areas where there's very reasonable formal type questions and specs one might ask about a neural network. You could ask about robustness around training examples and validation examples. So there's this concept of adversarial examples to neural networks. It turns out that for some reason, when you have a picture of a horse that a neural network sees as a horse, there are sometimes ways of changing just a pixel here and there in subtle ways that to the human eye, still a horse, like actually totally unrecognizable, you haven't changed anything. But you can make the neural network say, no, that's a panda. So it'd be nice to know that there's some robustness that like you need a certain threshold of changes to the image to make it switch from horse to panda. That would be a nice, given the neural network, it'd be a nice thing to verify about it. Another example is neural networks are a popular technique in, well, they're an exciting technique in control systems and also games like AlphaGo or other search problems like that. And those are systems that do have kind of a formal spec. A robot obeys the laws of physics. You can try and model as carefully as you can with mathematical equations. And that's the classical approach of control theory. But the problems are so high dimensional and difficult that classical methods don't scale. So if you could have some reinforcement learning algorithm that somehow figures out some way to control this robot, that's great. And you could, in principle, try and attempt to verify that it actually is controlling the robot according to the model you have of the robot. Another possibility is neural networks as computational accelerators. There's problems we know how to solve, but maybe are slow. And So it may be useful to solve a bunch offline, train a neural network, and maybe because the implementation is just so great of these neural networks, they're just way faster than the more deterministic first principle way of solving the problem. And we could, again, check between those two implementations using some kind of formal method technique. Or another thing we could do is dead neuron pruning. We could prove that certain neurons never fire in the neural network. So here I'm going to take, just to give a flavor, an extremely toy problem. Z3 is not designed to verify neural networks. I'm just showing sort of how you might model this sort of thing to get the brain juices flowing. So the toy problem we have is we're making a one-dimensional function approximator. Neural network techniques are kind of the wrong method for this, but they do work. So we're going to fit a simple one-dimensional function and then verify the accuracy of that fit to the function. So this is nice for a couple of reasons. We can visualize it. It drives home the point. We can actually, and that drives home the point of neural networks being piecewise linear functions and how similar training is to just curve fitting, if you want to take sort of that mathematical abstraction of it. And it's simple enough that Z3 can actually solve it. Real world neural networks are huge. That's kind of their point. And it's pretty tough to scale a formal method up to that. Here's my spec function. My spec function is this cute little polynomial right here, which just so happens to be a Chebyshev polynomial. And here's a plot of it between -1 and 1. And then I can import TensorFlow. And I'm going to use the Keras interface to TensorFlow, which is kind of an easy interface to use. So my neural network is going to be one input going out to 20, spreading out to 20 intermediate nodes, then going through a ReLU, then going a linear transformation to 25 nodes, then going through another ReLU, and then a final collapsing of the 25 nodes to a single output number. Okay, and I'm just going to use stock Keras training functions, and we can run this hopefully. And there's our neural fit, and it looks pretty good. You can see here if you zoom in, you can see some You can see some corners there. So this is, in fact, a piecewise linear approximation. It's just a pretty good one that looks almost smooth. It's so refined. OK, so how can we turn this into a Z3 query? Well, we can get the weights from the model. So these are matrices of those linear layers, matrices and offsets. We can define a ReLU function in terms of Z3. This is, again, if the input is greater than 0, return the input. Otherwise, just return 0. That's the ReLU. Here is the specific neural network. We said it was 3 layers with ReLUs in between. And here we're using the actual weights after the training. We instantiate the spec, which is that polynomial. We instantiate the neural network. We constrain the input to be between -1 and 1, which is the only region we're deciding to care about. And it was the only region we trained on also. And then the spec is we're searching for an example where the absolute value of the predictions differs by 0.5. So if we run this, it may come back proven. It may come back that it couldn't find anything, in which case we verified that this neural network is accurate up to an absolute value of 0.5, or it may return a counterexample, unset. So that proves that this function approximator is an accurate representation of this function up to an error of 0.5. But 0.5 is a lot. So we can lower this. Let's say 0.2. It should still be 0.2, right? It actually looks pretty good. So let's see what happens. Sat. Cheb. So it returned a bad value, 63/64. Apparently, if you look at this thing, actually the edges don't look that good. if you look carefully, over here and over here. And 63 over 64 is pretty close to 1. So it's a counterexample that's occurring somewhere around here. And in that region, we in fact are less accurate than 0.2. So, this is a current research topic because everything related to neural networks is a current research topic that gets people excited. But for more on this sort of thing, you could check out, there's a recent 3-part tutorial at the SAT SMT school by Guy Katz. And he's, I think, a leading figure in sort of neural verification. And there's also this Julia package, which is interesting and has interesting references in the README. And they implement a bunch of different verification techniques for neural networks. Again, Z3 is not the appropriate tool for this. But there are things that are similar to SMT solvers that are designed for this, or perhaps are taking a more specialized solver approach to this problem. So with that, that is all I intended on covering today. So takeaways, Z3 is super fun. Is an extremely powerful solver with a super flexible like input language and excellent bindings. You can use it to satisfy constraints and solve puzzles. Exhaustively failing to find counterexamples is what we mean by proofs in this context. You can apply Z3 to sort of pure mathematical problems like properties of the reals, or you can have more abstract algebraic type problems you can talk about groups or monoids or things like that. And Z3 is also designed from the get-go to be very applicable to programming style problems. It has support for bit vectors, it has support for floating point numbers, it has support for arrays. And really that's its bread and butter. Having said that, Z3 is not a panacea. It has some weaknesses in regards to abstraction and induction, some things that a pure mathematician, very natural questions for pure mathematicians don't encode so great into Z3 because they like to take an extremely abstract perspective about what they're doing. But these things are the strengths of interactive theorem provers like Coq, which Cody is going to talk about tomorrow. Nevertheless, if you work to Z3 strengths and make small compromises in what you're proving, you can do really astounding stuff with minimal effort with Z3, doing a lot of the heavy lifting. And so with that, thanks everyone for coming. We'll take questions. And here is a list of references, some really interesting stuff, I think. So here's a Z3 tutorial. Here's a Z3 Python tutorial. A fascinating sort of next level document is this programming Z3 tutorial by the developers of Z3 that gets some really interesting in-depth examples showing the powers, the modeling power of Z3, and explanations a bit of how it works. Another developer of Z3s gave a tutorial. Here's some constraint satisfaction solving problems. Dennis Yurchev's is an incredible resource. I think he's actually at the conference. I don't know if he's in this session. So if you Slack him, you can talk to him. Some more videos. There's a SAT SMT school that has some more videos about how SMT solvers work a bit. Get more to that. All these courses sort of have more about the nitty-gritty of how these things actually work. And with that, I'll take questions.
So at a very high level, Z3 is about solving SMTs, SATs, and the other one, Coq, is about proving theorems. Yeah.
So Coq by default is not very automated. The great thing about Z3 is that it does a lot of work for you. Like you sort of figure out a way to phrase your problem to Z3, and that's kind of the work you're doing. And then Z3 does all the solving. But in Coq, as you'll see tomorrow, an even more flexible language to describe things to Coq. Coq has an extremely flexible language to describe things to it. But because of that, you lose the automation. But that flexibility is at a certain point, at a certain level of difficulty, a problem you want to talk about, you need that flexibility of being able to discuss things And it's just basically impossible to automate it to a sufficient degree, although it's a current research topic to try and automate interactive theorem provers like Coq as much as possible. And Coq does have a plugin, for example, that can call Z3 to discharge certain proof obligations. And other interactive theorem provers also have things like that. They can call Z3 and other automatic theorem provers. And also there are languages within these systems typically that you can write your own automation. It's sort of a different level of expertise required, though, in my opinion.
I mean, do you think it's incorrect to think, the way I think about it is that these theorem proving assistants tell you what you need to prove, where a SAT solver will prove something for you?
Yeah, I think that's fair to say those are their strengths, that you are still telling Z3 a logical statement, but it's less flexible in the logical things you can enforce to Z3. But the Coq and other systems have extremely flexible input language.
Yeah, I mean the community overlap is huge, right? So
the community overlap is huge, but yeah, people really do sort of tend to specialize in one or the other.
That's fair. So the dream is, yeah, you see a theorem, you press a button, it says yes, no, with a counterexample or an actual like verifiable proof. But that dream is very far, and like Z3 gets you, from the bottom up, and Coq goes from the top down, right? So in Coq, you tell it everything except a few things that it knows how to do itself. In Z3, you can't give it any hints, but it's limited in what it will allow you to ask.
So sometimes I like to think of this as sort of a spectrum of automation, where you can start with like absolutely nothing being automated, and that's kind of where Coq starts. Or you can start at Z3 where everything is automated, and then you push in both directions. In Coq, you have these tactic languages that let you sort of automate obvious proofs, or they can shell out basically to external automated theorem provers. But then on the other side, there's also sort of, you can, instead of making your query just one big bulk Z3 query, sometimes you separate sort of sub-problems out to Z3, and then you sort of have a external program that you wrote that sort of understands how those pieces sort of weave together to prove the property you actually care about. So some of the systems that I have links up for there, they don't, most of them, some of them just build a giant Z3 query and dump it into Z3, but some of them build like individual post-condition, precondition verifications and things like that. And then they internally reason about how to compose those things. So you can push from both directions, and they sort of meet in the middle a little bit.
Would you also put F star there, where like it's the contract there, right? If I understand it correctly, is that you give it total functions, and Z3 proves that the function is total, and that it can use those to prove the correctness of the program.
My impression of F star, which I don't know too much about, but is that it's a little bit closer to the unautomated side, but its whole point is to try and be as automated as possible as a sort of formal interactive system can be. So it's kind of in the middle, but a little bit closer to the interactive theorem prover side.
Question, if we're done with that.
Yep.
So first of all, thank you so much for the talk. This is the tutorial. This is the earliest I've woken up all quarantine, and it was worth it.
Oh, that's high praise.
So I know that Z3 is used a lot in libraries for things like liquid Haskell, or like a lot of theorem provers shell out to it, a lot of different things. If I was, say, not writing tooling or libraries, but writing an application or an enterprise work, when should I be thinking, maybe I should start like encoding this problem in Z3?
So I guess there's two answers to that. There's sort of, sometimes constraint satisfaction problems are a thing where I've sort of hand coded Z3. I've used Z3 capture the flag competition for like, this occurs where like you need to find an input that does something. Okay, neither of those are enterprise settings, I guess. I think by and large, it's more trustworthy for you to be using someone's tool that caches out to Z3. And I think if you're not building formal methods tooling, there's less opportunity for you to use Z3. But I think the most
Challenge accepted.
But now that you know sort of the things you can express to it, if you come up with little subproblems or constraint satisfaction problems, or you need to like build a roster for your enterprise team that satisfies some constraints or something. The big issue is that when you're hand translating correctness properties from your program to Z3 and not using a tool that already sort of was careful about it, it's pretty easy to screw it up. So it's kind of maybe a false sense of security, like, oh, I'm using these formal methods. If you're doing this hand translation, like your translation is now the weakest link there. So I guess that's my answer to that.
Thank you.
I have a question. So SMT solving is, research in development and is constantly growing. How does Z3 keep up with that research?
Well, it's still actively developed. And I mean, the Z3 is like world-class, like the brand name in SMT solving. Like it's the one to beat, kind of. I don't really know what's on the horizon for SMT solving in terms of like what's an exciting thing that's coming down the line. One exciting thing is that the SMT lib 3 standard is at least in draft phase. And so there's some talk of currently Z3 sort of supports first order logic. But I think it's in the cards eventually for SMT solvers to sort of work over higher order logic, which is really exciting to me because sort of this first order to higher order is one piece kind of the expressivity difference of SMT solvers versus interactive theorem provers. Like the higher order logics are vastly more expressive. Another thing that's interesting is sort of SMT solvers for real, more continuous problems. Like Z3 supports real numbers, but its language for expressing constraints over the reals doesn't include sines and cosines and things like that. And sort of an interest of mine is sort of control systems and hybrid systems. And so for that, there's other SMT solvers that sort of have features more geared for that. So that's an exciting area for me. Z3 is world class.
I saw some research. Cool stuff about like regular expression reasoning, which is actually somewhat tricky and is this hilariously large proportion of like, site destroying bugs are like poor.
That's interesting. Z3 does support regular expressions currently. I don't know how good it is, but the input language does support regular expressions.
They have been working quite a lot lately on string solving, and I think that actually there are some nice projects on doing verification of JavaScript using those.
Cool. Does that answer your question, Greg? Roughly? Yep. I mean, Z3 participates in the competition, which I think is, that competition, the SMT solver competition is where all the SMT people get together and say, this is what we should be fast on. Sometimes that's a bad thing, but usually that's like, it keeps everybody kind of up to speed.
I think, in fact, Z3 is no longer submitted to the competition, but it's run by default because that's the comparison everybody wants to know about. So it's there. It's just it's not actually in the competition, as in I don't think it can win.
It's pretty baller though, right? Because sometimes it wins anyway.
Yeah. But there are problem Z3 is just has so many features to it, and it just sort of has the widest spectrum of support for different things. But there are subproblems that other solvers are better, as far as I can tell from the SMT competition. As a personal anecdote, Boolector is a different SMT solver that is more focused on just bit vectors, and it seemed to outperform Z3 for some problems I was dealing with.
That answers my question. Thank you.
Yep. Not by too much, though. Z3 was still very competitive.
Is there a good place to go to look at these various specialized ones to see if one fits your domain better?
Yeah, so there's I'll post a link in Slack. There's the SMT-lib website, and there's the SMT comp website. And it's sort of hard, probably for someone who's unfamiliar with this stuff, to pour through these, but because there's sort of these acronyms that are like, what the heck does that acronym mean? But the acronyms are combinations of sort of theory support. Like A means that it supports arrays, BV, I think it means supports bit vectors, etc. And if you go to the, oh yes, I did mean that, to go into the channel. So there's this SMT comp and SMT lib, and these are interesting resources to sort of reference material to sort of go through to see what's supported, generally speaking. Although Z3 supports more things that are in the SMT lib standard. So like I think the regular expressions, I don't think that's in SMT lib, for example.
Out of curiosity, how does Z3 allocate a budget for solving a problem? It seems like some problems they give up fairly quickly, but it was willing to chug through the long sort kind of problem. How does it allocate how much time is spent on a problem?
So I think it basically just runs forever, although you can give it timeouts, but we haven't today. It returns unknown when you've given it a problem it just doesn't know how to reason about. Or it can also return unknown if it sort of knows it's reached it's like stuck. And that happens, in particular, I've noticed that happening when you have quantifiers, which is also something I didn't discuss today. That sort of it knows it can't instantiate any more quantifiers, but it still hasn't really proven anything. So it's just sort of stuck and it returns unknown. Yeah.
In general, understanding how fast Z3 will give up or how much it will try is something of a dark art. There are lots of flags to tweak this, lots and lots of flags. Generally, all those theories that are in the SMT lib proper, which is linear arithmetic, uninterpreted functions, SAT, all that, Z3 will try its darndest. And everything that relies on nonlinear arithmetic, quantified logic, that Z3 will use heuristics to figure out how hard it's going to try.
Yep.
Do you see much interplay between like SAT solvers and binary optimization tools? In other words, instead of denying that P and Q could be true, say P and Q is some weight and find the minimal combination of variables. Is that
right?
Something in those worlds?
I mean, this is a world that exists. One key buzzword for that is MaxSat. Sometimes what's that called? Z3 does support optimization problems. I personally haven't explored that too much. And I kind of, yeah. So it does support that. And here's, I'll post this link in the Slack.
Okay.
you can say, set weights and set an objective function and ask it to minimize things. My intuition, for whatever that's worth, would be more inclined to go to a constraint satisfaction solver or mixed integer programming solver or a different family of solvers. There are also specialized maxsat solvers that you could try out.
Sure. Okay. No, I'm just curious. My world is right now quantum computing, which is a fully buzzword compliant and hype-driven industry, and quantum binary optimization things are one problem they can't solve. Whether they can do it better than classical is fully up for debate. And just looking at interplay between that and different worlds, and wondering, you could probably use a binary optimization solver as a rich man's SMT solver and spend a whole lot of time and resources to get something you could do in a fraction of the time with Z3. So I was just wondering, looking at interplay between the communities.
Yeah, I mean, everybody's talking to everybody, hopefully, and trying to steal everyone's tricks.
Or honestly, just notations. I really like you're right, the Python bindings for this are absolutely marvelous. They're a very good way to concisely express something, and that's just nice to see.
Yeah. Anyone else? Any other questions? Anything?
There was a question on the Slack by somebody on the wait list. The question was basically, you have a region that's described by some constraint, and you want, say, to like find a function that just explores that region. How would one go about doing this? Is it possible? The example given was, x squared minus y plus 9 is less than 0. And then what they wanted was x greater than 3 and x greater than minus 3 and x less than 3, right? So I guess it's give me some region for x that satisfies this constraint.
Where is this question? Is it in general?
It is in Z3 day 1. It is just a little bit higher, asked by Talis Macedo Garizzi. I'm not sure I'm pronouncing that right. So certainly behind the scenes, Z3 is absolutely maintaining constraints on X, right? As it's trying to find satisfying assignments. It doesn't print those out typically.
Okay, I see. They want a symbolic representation of the region, like a simplified.
Yes. Yes.
So Z3 does have a simplification available. So that was in one of my sections that we skipped over. I don't know if this is exactly will get you what you want or is exactly what's being asked, but you could attempt to run something like this. For example, this has some combination of regions, x plus 1 is greater than 3, and then some complicated constraint, and Z3 is capable of simplifying those inequalities a little bit for you. You could also use, depending on the region you're talking about, you could have some sort of loop where you use the solutions from Z3 to sort of build out the region.
Yeah. Do branch and bound basically.
Yeah. Like if you have a if you have a set of linear inequalities and you wanted to like figure out, really you'd want to use an optimization solver. You could
also have a Z and then try to optimize x greater than Z, and then
okay, that's true. So you could sort of like maybe start building a hull of a region or something using Z3. Okay, I think we're at the end of time. Thank you everyone for joining me. This is exhausting, I'm sure, but also fun. And so everyone is welcome to join the gather.town, encouraged to join the gather.town to socialize and talk to each other and share what what you do and what you want to use Z3 for, or what you want to get out of this conference. And thank you.
Thank you so much, Phil. Thank you all for joining. And again, let's thank Phil for this wonderful tutorial. Thank you, everyone.